Okay, question 3. This is another interesting question. So in the classical linear regression chapter, I gave two examples to estimate the model. One was the OLS, the other was MLE, like Bayesian likelihood estimator can be used if you additionally assume like normal distribution. But now we may apply the GMM to estimate the same model, right? Let's think about it, right? So remember, the moment condition we have is this, and the dimension is k by 1 and 1 by 1, so 0 should be k by 1, 0. And then from this, you can define xi times yi minus xi transpose beta. Okay, so remember, like GMM, we are going to define like beta hat as a minimum arg mean of transpose w hat n 1 over n gi beta. So this is GMM. Compare this to OLS, right? So GMM and OLS. OLS looks like this. It's so as you see, they are different. So even if W is just identity matrix, so even if W is identity matrix, then think about this. Then you can write that as like if X is scalar and W is identity matrix, the GMM minimization problem looks like this. So in the least squares, square is taken first and then summation is taken. But in GMM, summation is taken first and then taken squares. By the way, another difference is here. Its first order condition is this, so they are related, but minimization problem is different. Okay, so anyhow, let's keep doing this. We are going to show the equivalence in the end. Part B. So the derivative is pretty simple. It does not depend on beta. So G should be like minus expectation of xi transpose. And of course, rank of G, capital G, is K by the full rank assumption. That's simple. C, omega is expectation of Gi beta 0 times Gi transpose beta 0. That is expectation ui squared xi transpose. Okay, so this is omega. And if you have homoscedasticity assumption, then you may write it as this form under homoscedasticity, but you can think them as a separate case. And part D, again, supremum of the derivative is pretty simple because the derivative does not have beta, so supremum does not do anything. It is just the constant, right? So you just take expectation of this guy is expectation of this, which is finite by another assumption. So this is pretty simple. And part E. So here it's tricky. What is the optimal weighting matrix? Weighting matrix W, actually it is a trap, right? So you do not need to think about the weighting matrix because there are k moments for k unknowns. So W doesn't matter. This is the right answer, right? So you may, if you use this or this and its inverse, that is okay, right? So if you take the optimal, like the variance and its inverse, that is still okay, not because that is optimal, but because W doesn't matter. No matter what you do, the solution does not change. So it is okay, but it is a stupid way because you are doing additional work that is unnecessary, right? So the correct answer to this question is W doesn't matter. Or then, so you can say that W can be identity matrix, right? Identity matrix can be used as W. All right. Then let's think about part F. So we are going to consider identity matrix, okay? And then the first order condition looks like this. The first order condition of the GMM problem will be like this. W will be ignored, W hat, and I will just write the general form. This will be 0 in general, so 2 will be multiplied here, which is not a problem. So this is the first order condition, and then we are going to plug in 2 will be deleted, right? And the left hand, like the first term, will be xi transpose. Minus sign will be also ignored, it doesn't matter. And W is identity, so you can ignore that. And here you have xi times yi minus xi transpose beta hat, right? It is 0, right? I am going to denote, so let's denote xi times yi as an, and I will denote this guy as bn, okay? Then what you get here is bn transpose times here an minus bn beta hat n is 0, which implies bn transpose an equals bn transpose bn beta hat n. Okay, and now think about this. Actually, bn transpose is bn, right? X transpose is symmetric, so it doesn't matter. And also bn converges to expectation xi transpose. It is non-singular. So we can just invert, so we will ignore the transpose first, and then we will multiply bn inverse on both sides, right? Then you cancel out this and this. And then multiply bn inverse again, and then you will get inverse times an, right? So think about this. It is exactly OLS. Right? Very familiar OLS is the solution, right? So the GMM is equivalent to the OLS. And by the way, even if you used a weighting matrix, that also does not matter because Wn will be here, Wn will be here, and Wn will be here, and here, or n here. Just what you need to do here is just multiply W hat inverse once more. In the end, it will be cancelled out because W hat n converges to W that is non-singular, right? By the same logic, W can be ignored in the end, so you have a closed form solution like this. So this is very strong. By the way, then you may ask that, okay, then can we compare the variance? Obviously, right? Variance should be the same because just how you calculate the estimator is the same, right? So the equivalence of the variance follows from this strong result. Okay, so we learned GMM as another possible estimator to estimate the classical linear regression model here.